Swayam Prabha. Digital India. Educated India.
Okay, so last class we had started on dual converter. We in fact migrated from the discussion of the DC to AC conversion using the same thyristor converter when we make alpha greater than 90. We said when alpha is greater than 90 in an SCR converter, we are normally going to see that the DC voltage reverses. But we are not going to have a reversal. We are not going to see a reversal in the polarity of the current. So IDC will not reverse. IDC will not reverse, but VDC will reverse. So VDC times IDC reverses, which means power flow is from DC side to AC side. But if the power has to flow from DC side, that means the load has to be active. That's what we said when we were talking about a single converter when it is feeding a DC motor drive, and if the DC motor drive speed has to be reduced, let's say we want to brake, we want to reduce the speed of the DC motor drive, in that case we said that the kinetic energy stored in the machine's rotating parts, that can actually drive the machine as a generator. Rather than the machine working as a motor, it will start working as a generator, because of which the power could be fed back to the AC mains, provided we make the converter conducive for the operation as feeding back the power from the DC side to AC side. For that we said alpha has to be greater than 90. So we actually took an example also saying that if this is my overall converter, which I am showing in the form of a block diagram, if I show it like this, and this is my three-phase input, and here is the DC motor drive which is connected. So originally when I might have connected this as a motor, I would have had A here and B here, so plus and minus somewhat like this, with the back EMF being EB here. Now the current must have flown from this portion, which is VA, the armature voltage. The armature voltage, what is available depends upon what is the value of firing angle at which I am firing this converter, and what is the kind of AC voltage that I am having. So I am going to have the voltage here VA to be 3 Vm by pi cos alpha, as per what we derived earlier, if it is a fully controlled converter. So maybe this VA is 220 volts and the back EMF is 210 volts, and then I am going to have the current flowing in this particular direction, which is actually my IA. So the power is flowing from the AC side through the converter to the DC side, which we call as the normal motoring operation, right? If I want regeneration, so this is motoring operation, and if we want really the generating operation, maybe we will need it when we want to reduce the speed of the motor drive. We don't want to waste the energy. So we want to reduce the kinetic energy by converting that amount of kinetic energy into electrical energy, if it is possible, so that we save on some amount of electricity indirectly. So in that case, we may have to have again, this is my converter. I am not changing the connection of the converter electrically. It is the same converter, and I am having the three-phase supply here, and here is my motor drive, and this is how it is connected still. But only thing is that I want to make this alpha greater than 90, whereas here the alpha was less than 90. When alpha was less than 90, I was having plus here and minus here. When alpha is greater than 90, the same cos alpha is going to become negative, because of which this will become plus and this will become minus. So, if I make alpha greater than 90, I will have plus here and minus here for the same VA. But the direction of current cannot change. The direction of current has to be still the same, which means the current has to flow in the same direction. But I will be able to change the direction of the back EMF by either reversing the armature terminal, so I can make A here and B here. If I disconnect and reconnect, yes, it will take some time. It will definitely have a large current being interrupted and again reconnected. These are hazards, no doubt. But we have to weigh basically what is the advantage we get in terms of feeding back the power vis-a-vis what is the kind of hazard that I am going to face. So if I am able to handle it, I would be able to feed a significant amount of power. So I would like to rather experiment with this and then make A and B in the reverse direction. So I am going to have plus here and minus here. Please remember, I have not changed the field current direction. I have not changed the speed direction. Speed might have been at 1500 RPM. I want to bring it down to 500 RPM or 0 RPM. Depending upon at what point I want to stop, and then go back to steady state operation. But I am not changing the direction of rotation. Because I am not changing the direction of rotation, back EMF now will have plus and minus in the opposite sense because of simply reversing the armature connection. Now, if it so happens that originally this was 220 volts and this was 10 volts and maybe alpha was 80 degrees, this is what we had taken earlier arbitrarily. If now I want to have the same 210 volts here, it is still 210 volts because I assume that the inertia of the motor drive is not small. The speed will not change significantly quickly. So this is 210 volts. So if I want the current to flow from this plus to this plus, that is the machine's plus terminal to the plus terminal of the line commutated converter. I am not calling it as a rectifier anymore. I am calling this as a line commutated converter. So line commutated converter is a general term used for either a rectifier or an inverter which will allow power flow from the DC side to AC side or AC side to DC side. But normally it will be made up of SCRs, thyristors, because they will require some kind of reference for firing. So if I say alpha is less than 90, I would call that as a rectifier or line commutated converter working as a rectifier. Or if alpha is greater than 90, it will be a line commutated inverter. Okay. So in line commutated inverter, you will need a sinusoid. The reference sinusoid has to be there. If the reference sinusoid is not there, you don't know at what alpha you are operating. So you should know that you are operating at an alpha which is greater than 90. So in this particular case, I might have to operate it if I want equivalently the same amount of 220 volts if it comes, but with plus minus in opposite direction. The current will not be able to flow from here to here because this is 210 and if this is 220, the current cannot flow like this. So it has to be less than 220. It has to be much less than 220. So instead of 210, instead of 220 here, I might have to have 200 or 190 or something like that. For which, instead of having an alpha of 80, I should have probably had closer to 90. Only then I would have had lower and lower voltage. Right? So I might have to have just alpha equal to maybe 92 degrees, 95 degrees or something like that. It is still greater than 90, but it is not really equivalent to having, like 80 degrees if I want to have exactly. On the other hand, I should have had 100 degrees. Cos of alpha equal to cos of alpha in one case is cos 80, in the other case it will be cos of 100. But cos of 100 will be a negative value. But I don't want that value. I want it to be less than that. So that's why I should have it closer to 90 degrees, as close as possible to 90 degrees. In which case, I would be having less amount of voltage here. So the current would start flowing like this. So this is typically a line commutated converter operation. This is how it is going to work like an inverter. So this machine is having 210 volts at this speed. Now because it is 95 degrees, the current will start flowing like this. Now because this is generating power and releasing the power in the form of electricity to the three-phase grid, the speed will come down further. The speed will come down from maybe 1500 RPM to 1200 RPM. By then, EB would have decreased again from 210 volts to maybe 208, 205 volts, whatever. Then correspondingly, I might have to again go more and more towards 90 degrees. So, I have to constantly adjust, repeatedly adjust the firing angle as per EB, and EB gets adjusted as per the speed. So, theoretically, we will be able to achieve regeneration almost down to zero speed if we are able to adjust all of them in a very fine manner. Right? So, you should know that this particular operation of the line commutated inverter, that is an SCR rectifier working as a line commutated inverter, allows you to feed back the energy and then, allow you to undergo regenerative braking using your DC motor drive, which can save a lot of energy. But that's when I think Shikhar asked, why not have two converters? That will do the job, and from which we actually migrated to dual converter. So coming back to dual converter, so this is motoring and this is regenerating, right? And here VA has to be greater than EB. Very clearly here VA magnitude has to be less than EB magnitude. I'm carefully writing magnitude because I don't want you to confuse yourselves with the minus sign and say which is greater, which is less and things like that. So I'm saying that VA magnitude has to be smaller, only then the current will flow from the EB side to VA side. Is that clear? Okay. Now let us go to dual converters. So in dual converter, what we said was that we are going to have one set of converter similar to what we discussed so far with respect to rectifier. Of course, it has to be fully controlled. It has to be fully controlled because we want the voltage to go in both the directions. It should be possible for me to do that. And on the other side, I'm going to have again a similar converter connected in anti-parallel direction. So the two are in anti-parallel, and I'm going to have this as the DC link. Maybe my load, whether it is a DC motor drive or RL load, it doesn't matter. This is how it is connected, right? And I'm going to have the three-phase supply connected here. So if I say this is the ABC of three-phase 415 volts, 50 hertz, the same thing is going to be connected here as well. So this is also the same ABC, although I'm showing two different terminals, but they are connected together. They are connected to the same three-phase supply. Now, one is fired at alpha 1. Let me call this as converter 1. And the other one is converter 2. And this is fired at alpha 2. Both are being operational. And we called this voltage as VD1, and let me call this voltage as VD2. In fact, I would have liked to connect these two terminals directly, but instantaneous voltages could be slightly different, like what we spoke about in DC machines, if you may recall, lap winding. When you have several parallel paths, the voltages could be slightly different. So we connect them together using an equalizer ring. And so it will be like a thick copper rod which is connecting all of them together. So it is something similar, that we are going to have probably a thick reactor coil which is connecting these two together. Let me call this as L and the voltage across this as VL. Okay? So we drew the waveform last time for alpha 1, which is coming out to be 60, but we also said that we want VD1 equal to VD2 under steady state condition, so that the circulating current does not become too much. Between the two converters, I don't want huge amount of circulating current coming up. So under steady state, this should be true, which means I should have 3 Vm by pi cos alpha 1 equal to minus 3 Vm by pi cos alpha 2. Right? So we wrote the equation cos alpha 1 plus cos alpha 2 equal to 0. So we said alpha 1 plus alpha 2 equal to 180 degrees. This is what we got as the solution for this. So if one is going to be having 60 degrees, the other one should be having 120 degrees. So similarly 180 degrees and so on. So if I assume alpha 1 is 60 degree, I am going to draw the waveform for that. This has to be drawn for alpha 2 equal to 120 degrees. That's how it can be drawn. Now, so let us try to first of all recall the waveform, what we drew last time also. So this is, I am going to draw with respect to 60 degree firing angle. So I hope so that you remember already, this is the way the 60 degree firing angle waveform would look like. This is how it will be. Right? So this is what is my VD1. Right? If I try to draw corresponding to VD2 as such, it is actually the inverse of minus VD2. And we drew for minus VD2 last time for 120 degree firing angle. It came out somewhat like this. If you actually recall, it was something like this. So it is just the opposite of this, but below 0. So the entire thing looks as though the whole thing is negative. So this actually corresponds to what is 3 Vm by pi cos alpha 2 without a minus sign. So this is essentially minus VD2 waveform. So if I try to draw the actual VD2 waveform, I have to just invert that. It is as though in CRO you put a 180 degree shift. That's it. So it is going to look somewhat like this. This is how it will be. Right? On an average basis, both these voltages will have the same value. If I look at the area under this curve vis-a-vis the area under this curve, they should essentially have the same area, because it's again the 60-degree span, and it is starting from probably 120-degree point in one case and coming down to 180-degree point. This is like 120-degree point of VAB, and then it is coming down to 0 because 180-degree point is that particular point. The same is true even in the other case, although it is starting from 0 and maybe going up to 60. That's all. Both are essentially similar. But instant to instant, if I look at the voltages are different. Here it is 0, whereas here it is maximum. And here this is 0, but here this is maximum. So if I look at the voltage at this point and this point, on an average basis, although they are the same, instant to instant the voltages happen to be different. Only point where exactly the voltages are the same will be somewhere in the middle, because in the middle, here as well as here, it will be, whatever is half the value or more than that, whatever is the value corresponding to that particular angle, right? So I am going to have the exact same value only at one particular point where both of them happen to be having the same value of sine of that particular angle, right? So if I try to draw what is the voltage across the inductance, VL. So let me try to draw that voltage. What is VL? So VL actually will be VD1 minus VD2, right? Whatever is the value of VD1 minus VD2. So VD1 minus VD2, if I try to look at it, only at this point it will be 0. So if I try to draw for every 60 degrees, only in the midpoint it is going to correspond to 0, and it is going to start from a high value which is corresponding to that Vm sine 120, right? So it is going to start from a high value, come down, and then come to the negative. Again do the same thing. It will repeat itself. This is the kind of waveform I am going to have for the inductance. Voltage. The voltage across the inductance is going to have some positive portion for half. For rest of the half, it is going to have negative, because I have to subtract from this value. I have to subtract whatever is the value that is available from the other VD2. So I have to realize that I'm going to have this portion, whatever is the area under this curve, will be equal to the area under this portion. So the net voltage across the inductance happens to be 0. If I try to calculate it even for 60 degrees, the voltage across the inductance is positive here, voltage across the inductance is negative here. So fluxing happens in one case, defluxing happens in the other case. So this is going to repeat itself until time immemorial, as long as it operates. So if I try to plot what is the inductance current, just the inductance current alone, forget about the load current. Inductance current is, it can be calculated using L di by dt equal to VL. So di, I should be able to say whether it is positive or negative. So if I say during positive voltage I am going to have increase in the current, during negative voltage I am going to have reduction in the current. So again increasing the current, reduction in the current, increase in the current, reduction in the current. This is how the current waveform is going to be. If I am looking at the voltage continuously increasing only for 30 degrees, decreasing for 30 degrees. Again increasing for 30 degrees, decreasing for 30 degrees. So I'm going to have the current also increasing for 30 degrees, decreasing, increasing, decreasing, and so on. This is IL alone. Of course there will be a load current. Maybe there is a huge amount of load current being drawn. The load current drawn is being supplied by the rectifier, it will also pass through at least part of the inductance, no doubt about that. But load current, if it becomes almost like a steady current, it is not going to contribute to inductance stored energy. Because LdI by dt only will be contributing towards the inductance stored energy. So, the steady load current will not contribute towards really storing energy in the inductance. So, if I look at the rectifier side current, that is converter 1 current, this will consist of IL plus I load. Both will be supplied by the rectifier. Whereas the other side, this is not going to carry the load current. This is only helping in making sure that that inductance circulating current is going back again to the three-phase mains. That will go through this to the three-phase mains. So, only the inductance component of current will be carried. So, this is converter 1 current is both these put together. Whereas, converter 2 current will have only IL, nothing else. You have to understand that if my converter, this converter had not been there, the second converter had not been there at all, still the load current would have been carried by the converter 1. So the converter 1 is just doing its job. It doesn't care about anything else. Whereas converter 2 is actually right now redundant. It need not be there. I have put it there only in case I want to reverse the direction.